how the electrons occupy the orbitals. So you have this periodic table here, and we are going to use this periodic table as a left to right, top down, how we go, atomic number. So what are the atomic numbers? 1, 2, 3, 4, 5, 6, and so on, right? 7, 8, 9, 10. Right, here's 11 through 18. Right, 19. Right, to 36. We're just going to go right in order. Okay, there are some anomalies here. If you look, this is 4, 3. That's 4. Right, there are some. I'll highlight them right now. Oh, that's not a good highlight for that color. 3, 4, 5. Right, these D's are off by 1. The F's are off by 2. We'll get there. Right, but the ground state's the lowest energy state and the most stable state, and that's what we're going to focus on. Okay, we're going to focus on the ground state. We're pretty much ground state. That's it. We're not going to do anything else. No, we eventually will get to ions in the ground state. So everything's ground state. Okay, and so we got the quantum numbers. Just recap. Quantum numbers. We had principal, right, which is our energy level. And the values n can be 1 to infinity. You have the secondary, L. This is our orbital shape. L can be 0, 1, 2, 3, all the way to n minus 1. Now we know S, P, D, F, right? S, P, D, F. So L is 0, S, L is 1, P, L is 2, it's a D, L is 3, it's an F orbital. Then we have the magnetic, M sub L, and this is our orbital orientation. And M sub L equals negative L to positive L. And finally, we have our spin. MS, this is an electron spin, and MS can be plus 1/2, which is up, or minus 1/2, which is down. That's it. So those are our numbers, and we're going to throw this in here. Now, there are two things with electron configuration. There is electron configuration, and orbital notation. Alright, orbital notation is almost always a box. A box represents an orbital. So this box, the box, could be a circle, depends, it could be a line, box, circle, line, right? That represents the orbital. One box or line per orbital. The arrows represent the electrons. So that's an arrow. That's an electron with ms equals plus 1/2. And this electron is an electron with the ms equals minus 1/2. Spin up and spin down. They draw the arrows that way. You can draw your arrows however you want to draw them. That's how a lot of people do them. The electron configuration goes with N, L, and then the electrons. That's how electron configuration goes. N, L, number of electrons in that orbital. Right? Because L is the orbital. So it doesn't differentiate, like we got 3 p orbitals. Px, py, pz. Okay? Now, it gets more complicated than that if you go on with chemistry. But if you're taking Chem 1, that's as complicated as we need to be. Alright, if you're taking physical chem or a higher level chem than that, then it gets into shapes and phases and all sorts of weird fun stuff. I enjoyed it, but it's not necessarily relevant for us. So we want the electron configuration and the orbital rotation. We're going to do these for some elements here. So hydrogen and helium, they're 1s, right? And we saw that picture up here. They're in the 1s. Hydrogen and helium are 1s. Okay, 1s. I like to color. Not really. I have kids. They color enough. Alright, so 1s. So hydrogen has 1 electron. We know hydrogen has how many electrons? Has 1 electron. We know helium has 2 electrons because that's its atomic number. Alright, in neutral hydrogen, 1 proton, 1 electron. Okay, so it's 1 electron. The first, by definition, first electron is always positive. First electron in orbital is plus 1/2. Up. That's just by convention. Is it always? No. Right? They can flip spin. We're just going to go up by convention. Our electron configuration, N is 1. It's an s orbital, so it's an s, and there's 1 electron. So that's the electron configuration for hydrogen, 1s1. And the orbital notation is just a box or a line. We could draw it like this too, where you have 1s here and up. Either way works. I'm happy either way. Okay. Most Chem 1 draw it with the box. As you get higher up, they start doing the lines, and that's okay. I'm happy either way. Helium. It's still 1. Still energy level 1. It's still an s orbital. But now there are just 2 electrons in that s orbital. So we'll look up and down. That's hydrogen. That's helium. That's it. Now I like to think of electron configuration as a big stadium seating, whether it's an actual stadium, whether it's like a stage, concert hall, something like that. Doesn't matter. There's just stadium seating. Up front and center is the 1x seats. There's 2 of them. All right, then there's the 2S seats, and then there's the 2Ps, and it just goes stadium seating, and everybody goes as front as possible. All right, I know a lot of people, when they go to places, they tend to sit in the back, whether it's a religious venue, whether it's a movie or a class, school. I sit in the back. Well, when I played college football, freshmen sat in the back. Seniors, front and center. Juniors, it didn't matter if you were the quarterback of the team, All-American, you were not in the front row if there was that many seniors. Front and center was seniors. All right, seniors, then juniors, then sophomores, then freshmen. That's how it worked. And everybody wanted to be up front and center to coach. All right, that's just good advice for you in general if you want to sit and be noticed. Front and center is how to do that. All right, so whether it's a job, whether it's class. All right, some of you might be going to a school where there's thousands of people. Right, or there might be 300 people in your class. Well, if you want your instructor to know you, sit front and center each time, and they will recognize you for that semester because you're always in the front and center. All right, and so lithium still has its 1s orbital there, right? So each atom has the same stadium, right? Or has the same arena to fill in. And lithium's going to have 3 electrons, right? So lithium will start off with 1, then it'll have S, and it has 2 electrons in 1s, and then it goes to 2, and it's in the S block, and it has 1 electron there. Alright, so we look at lithium, we got up, down, up. Alright, so lithium, if I come back here, lithium is right here. So, let me erase my amazing highlighter job there. We always start here. 1s1, 1s2, full, check. 2s1, then it's going to be 2s2. Then it's going to go to 2p, and then it just fills in top to bottom, left to right. So left to right, top down. So beryllium is going to be All right. 1s, 2, and then it's going to be what? 2s, 2. All right, and it's going to have its electrons up, then down, go to the next level, up, then down. So there we go. So again, N is 1s. All right, so if you look, each of these, and we'll get to this later, but this electron, the first electron I put in, has different quantum numbers than the second electron, that has different quantum numbers than the third electron, than the fourth electron. All right, so boron. All right, and I have the boxes drawn for us, or lines if you want to draw lines. Okay, so boron. We start with 1s, there's 2, then it's 2s2, and then we skip over to 2p1. So what do? We go up, down, and then up. Carbon. We go 1s2, right? 1s1, 1s2, 2s12, 2p2. All right. If we notice, carbon, right, has 6 electrons, 2, 4, 6. That always works out. All right. Up, down, up, down. Here is Hund's rule. Up, up. So the first one's always up, and then we're going to put 1 electron per orbital until we have to pair up. Okay? All right? Just like if you went to a movie theater, like if I used to go to the movie theaters, and a lot of times, I can't stay up late anymore. Or if I do, anyway, I would go sometimes by myself. Right? Especially if it was a higher rated movie that I didn't want little people coming downstairs for. And sometimes I'd go to the movies by myself, especially if my wife had no interest to go see the movie. And so I would go, and I would always go towards the end of the cycle. Right? I wouldn't go premiere night. I'd go way towards the end. All right, so there's several times I have the theater to myself. So you go in. It'd be weird if you go to the movie theater and there's one person sitting there, and you went and sat right next to that one person, and you didn't know him. All right, people might think that's strange, and they would be correct. All right, so same thing here. Now, electrons do not do human behaviors, right? Electrons don't make decisions. They're just going to go in one orbital because they're negative. They repel. One orbital until each orbital's got 1 electron, then they pair up. Nitrogen. 1s2, 2s2, 2p3. So as you can see, it goes up, down, 1, 2, 3. Oxygen. 1s2, 2s2, 2p4. Up, down, 1, 2, 3, 4. Then we go to fluorine. 1s2, 2s2, 2p5. Up, down, 1, 2, 3, 4, 5. And finally, neon. 1s2, 2s2, 2p6. All right, so up, down, 1, 2, 3, 4, 5, 6. There we go. All right, so those are the electron configurations for the first 10 elements. And again, we talked about predicting behavior. So let's take a step back, deep breath. And is there any behaviors when we look at the periodic table and then these electron configurations? Are there any behaviors up here that we know? All right. Are there anything I know about certain behaviors? Well, you may not know this, but group 1 here, group 1, these are what we call the active metals. All right? They're not found in nature by themselves. They're not. You don't find a sodium metal. You don't find potassium. Right? They're highly reactive. You can find them in salts as sodium ion or potassium ion, but you don't find just potassium metal in the ground. Whereas these noble gases are inert. They do not react. In fact, hydrogen, sorry, not hydrogen, that's active. Helium, neon, and argon do not react at all. Helium will react in space, He2, but not on Earth. Right? Krypton and xenon can make some compounds if we force them to, but they're very inert. They're very unreactive. Right? So, how does our model help predict this behavior? If we look, helium, right? Helium has N equals 1 full. Neon has N equals 1 and N equals 2, both full. All right? So we have full orbitals. Fluorine, what do we know about fluorine? Well, we told you fluorine likes to be -1. I don't know what I did. There we go. Fluorine likes to be -1. So, if fluorine gains an electron, it's now isoelectronic with neon. It has the same electron configuration as neon. If oxygen gains 2 electrons, B-2, it also looks like neon. If nitrogen gains 3, 1, 2, 3, if it gains 3 electrons, it looks like neon. Carbon could gain 1, 2, 3, 4. It could gain 4 electrons and look like neon, but it could lose 1, 2, 3, 4 and look like helium. Boron could lose 1, 2, 3 and look like helium. Beryllium could lose 1, 2, B+2 and look like helium. Lithium could lose 1 and look like helium. Helium is helium. Hydrogen, now hydrogen can lose 1 or gain 1. It tends to lose 1 more, actually. All right. Okay, and so what we have there is a pattern that helps predict the charges of these main group elements. All right? Because what we're going to learn here is that everybody in, I put SI down, not SI, S1. Everyone in group 1 is S1. S2 in group 2. P1, P2, P3, P4, P5, P6, except for obviously this is S2, right? And so our charges, +3, ±4, -3, -2, -1, 0. They match with what our electrons we think they're doing. Okay? And so something else, and then we'll end this one. If you look, neon, right there, if I draw a line right there, this is helium. Whoa. This is helium, right? So, which would be our noble gas core. So it's our core electrons. These guys, right here, the 2, these are our outermost S and P electrons, which we're going to call the valence electrons. And they're the ones that were responsible for behavior. So valence electrons are the ones that are responsible for behavior. So neon has how many valence electrons? 8 valence electrons. It has 10 overall electrons, but it has 8 valence, right? The core are 2 core, 8 valence. Fluorine has 2 core and it has 7 valence. All right. Oxygen, right there, has 6 valence. You can probably see a pattern here. 5 valence. Carbon has 4 valence. Boron has 3 valence. Beryllium has 2 valence. And lithium has 1 valence. Now, what about helium? Helium has no core. So helium would have no core, not core, and 2 valence. Right? Hydrogen has no core, 1 valence. Okay? So the core, well, how does hydrogen and helium have no core? Well, let's look at the periodic table here. The core happens to come from the noble gas in the period above you. Alright? So the core comes from there. So if I am this element right there, which that element right there would be boron, not boron, bromine, excuse me. So bromine, the core would be argon. Does that make sense? If I am chlorine here, my core would be neon, the one above. All right, so that's what the core is. So in the next video here, we will actually do a lot of electron configuration and actually get into quantum numbers, electron configuration, how we do it, and all that. And it'll hopefully make more sense. But hopefully this shows you how the electron configuration is, the pattern, core and valence electrons. And let me know if you have questions.